My name is Kristina and come from the University of Zagreb. And as Luka had mentioned, that the previous research deals with part of exact science and part of mysticism, and that's the same thing I'll be doing today. Because part of my PhD research deals with unattested theories, and I've decided to take some cosmological unattested theories and see what will come up when I combine these things. Because I'm a philosopher, we do that. Okay, so let's start. Okay, I love this quote, and I wanted to start with it because today we have lots of problems to explain how did we end up in here, how did the universe start, and the inflation theory is one of the most beautiful theories that explains certain problems in cosmology that we have today, and I really enjoyed reading about it, and I wanted to present it in a way that it could be combined with philosophical research as well. So let's see what are one of the most important philosophical and cosmological issues that we have today, which Professor Bilic has already triggered a bit. So let's see. The first question is, okay, why is the universe so uniform regarding the large-scale structure? Okay. If I take a particle here, and if I take a particle 100,000 light years away, it will have similar physical properties. It will have similar spins, temperatures, and so on. So why is that? We would not really expect that. And that's the so-called horizon problem. And we'll get back to it later in a whole lot more detail. The second one is, okay, why is the geometry of the universe almost flat? We would not expect that. We had like 200 years of geometrical research. We had conspiracy theories regarding Gauss and Bolyai and Riemann and so on. And we had non-Euclidean geometries. And we have general theory of relativity, which kind of deals with various non-Euclidean geometries. So why is the universe so close to being flat? The third question is basically the one that we philosophers love the most, and that is, where did we come from? Where did these large-scale fluctuations come from? Okay, if we have these homogeneities all around, and everything is pretty much uniform, okay, but we have some scales which are non-uniform. We have planets, we have stars, we have galaxies, we have clusters. So how did we end up like this? Okay, so a long time ago, as we had mentioned already, Einstein believed that the space was static, and he wanted to defend his cosmological model. So if the things don't work out, he figured out that the gravitational impact would be too huge, and the universe would have collapsed. So he put the cosmological constant just to balance things out. And after Georges Lemaitre, Henrietta Leavitt, and so on helped Hubble figure out that the universe was expanding, Einstein figured out, okay, this is pretty much true because we know that the universe is expanding. So he called it the biggest blunder of his life. And we philosophers tend to do things like taking someone's trash and see what we can do with it. And one man's trash, and of course, is another man's trash and vice versa. But the scientists did that as well. So, okay, we have this cosmological constant. It seemed like the biggest blunder of his life. But what is it? Okay, it's the value of the energy density of the vacuum. It should be something like a negative negative gravity, anti-gravity, if I may say so. And it implies negative pressure and vice versa. But can we use it? Can we do something good with it? Okay, so the theory of inflation uses the option that gravity could be a repulsive force. So it's a repulsive force which is pretty much the thing that drove the universe in the period of expansion. So to have this repulsive gravity, we require negative pressure. And we had this small part of repulsive gravitational material, and it existed in the early universe and led to the creation of everything. Okay, so one blunder and creation of everything, that's a pretty huge step. So this is Alan Guth, my biggest hero, and he was one of the proponents of the inflationary theory, which is pretty much a model of the exponential expansion of the space in the universe. So it happens somewhere from 10 to the power of minus 33 seconds to 10 to the power of minus 32 seconds. And the universe expanded at a rate for 10 to the power of 25 times. And afterwards, this expansion continued, exponentially, of course, as well, but with a less accelerated rate. So we'll see later why did this happen, how did this acceleration change, and so on. Okay, this is the so-called inflaton field, which we need, and it sounds like a cool name for a killer robot like Inflaton. And when the universe was young, this field went over a large range of values, so you had a zero average value. But as their energy level drops, we have to go either positive or negative. That's basically, if I were trying to balance a pencil or this microphone on top of my finger, it wouldn't last for long. Or, for example, if I wanted to put a ball on top of a hill, if it was flat enough, the ball could stand, and it wouldn't roll down the hill or something like that. So this is the graph, which is usually called the Mexican top hat or the sombrero graph, and it really doesn't look like that. Okay, but this is the inflaton, and it consists of relation of energy and the strength of the field. So we are kind of looking at the middle and see what happens there. Oh, sorry. Okay, so this is the so-called false vacuum state. And it has millions times more energy than the rest of the observable universe, and it has that property of negative pressure. That means we'll have huge densities, and cube, centimeter, or millimeter would have like 100,000 more energy than the whole observable universe. So that's the false vacuum state. The real vacuum is on the value of 0. Okay, so, oh God. Gravitationally positive material is unstable. So this is a huge unstable material, and it usually turns into a non-repulsive one. Particles are produced, the universe grows extremely rapidly and grows exponentially, and things start to happen. So let's see how our theory of inflation can actually solve problems. Not really the Zimbabwe inflation one. I had to add that, sorry. So basically, we will go back to the horizon problem, we'll go back to the flatness problem, and the third, the so-called perturbations of density problem, but it's basically where the things come from. It sounds better like this, and I'm totally going to use it in class. So to introduction in philosophy, if you use perturbations of density problem, it sounds a lot cooler. Okay, let's see the horizon problem. Okay, so as I had mentioned before, usually different objects have similar properties if they have been in contact at some time. But our standard Big Bang model pretty much does not deal with that. So, okay, how can we explain that? And how can we even know that everything is uniform? And that's a story which I like to describe as a story of pigeons, murder, and deceit. So a long time ago, in the 60s, Penzias and Wilson were trying to catch some radio waves using their horn antenna, and they got some noise, that weird noise, and it was constant, and they tried to see what was the source of it, and they soon discovered, okay, we had a family of pigeons in our antenna. It's probably their feces which is blocking our signals, so let's clean it up. They shot the poor pigeons, which are not forgotten. I'm a huge proponent of these pigeons. And afterwards, they got the same noise all over again, so they contacted some researchers in Princeton, and they soon discovered, okay, this was one of the earliest things we can detect. These were the photons that started traveling towards us from when the universe was 380,000 years old, because they were coming towards us, and we saw this huge uniformity, and laterwards, we saw that it was truly uniform, and that was strange. And inflation solves these problems by postulating, okay, before the expansion of the universe, you had this inflationary period, which you can see on the graph. So the regions which are separate today, they have been in contact before the exponential growth of inflation. So we would expect similar properties. The second one is the flatness problem. Recently, Wilkinson microwave and anisotropy probe measured that the universe was flat with a margin of error of 0.4%. And that's pretty much weird. Okay, so why is that? If the universe was slightly curved at the beginning and it grew exponentially, we would expect that this curvature grew exponentially as well. So how can we solve that? So inflation says, okay, but the whole universe was enormously stretched out. So the original curvature was perfectly flattened out. And while in that field, energy density was constant, everywhere else it was decreasing. So it became negligible. And in this masterpiece I created in Microsoft Paint, you can pretty much see how this happens. Okay, you had a small curvature. When you stretch it out, it will become negligible. So basically, if you started with a curvature of space and time, if you started with, say, hyperbolic geometry of a spherical one and so on, it will flatten out because the exponential expansion grows rapidly. So if you remember high school, or sorry, most of you are physicists, so I'm kind of used to the phrase, if you remember high school. Please don't be offended. The exponential function grows rapidly. So this is the thing I'll need later for my research because I deal with computational complexities, and it's a huge bugger to deal with exponential complexities. So the third one is pretty much that cool title, perturbations of density. So we have homogeneous state regarding the large-scale structure, but what about these lumps, these planets, these stars, these clusters, and so on? And that's pretty much similar, okay? So inflation says this expansion increased the quantum perturbations, fluctuations, because these primordial seeds became bigger and bigger. Why? Recent studies found out that in the cosmic microwave background radiation, you had 1 part in 100,000 non-uniformity. So that's pretty small. However, if you start with this, and it grows rapidly, it grows exponentially, you'll get huge structures. So basically, it's unstable, and the excess of matter creates a gravitational field which attracts more matter, repeat, wash, rinse, repeat, and so on. So the inflation says, okay, it's pretty much easy. So the question now is, okay, is it a test that, yes and no, and yes and no? How can we really say that the inflation happened? There is a nice thing that we can do, and that's the so-called gravity waves. So inflation creates not only fluctuations in density, but in gravity as well. So these are the so-called quadruple waves. That's basically if you take, say, a lump of clay and you squash it, it will be wider, but it will be smaller, like this. So they're creating various polarizations in radiation. So they're changing and locally deforming the space perpendicular to the direction of its movement. So if we were to be able to detect this polarization, if some certain physical properties, certain radiation would be stronger in one direction than the other, we would say, okay, so this is kind of a confirmation. And they dealt with the so-called B mode polarization, which I completely don't understand, but it sounds cool. And you can ask Professor Bilic for everything involving this lecture. He will be glad to answer it because he knows a lot better than I do. And first results were pretty much inflation did happen. We have certain implications that it did happen, and then they said, no, it seems inconclusive, so we're still waiting. And it's kind of a dramatic situation. So every month I check out, did we have any new findings and so on, but 1 week you have, yeah, it certainly happened, we detected strong gravity waves, and the next week you have, no, this was some noise, and so on, so let's see. Okay. So, this Wilkinson microwave spacecraft measured that the space is nearly flat. What does that mean? So that means that the ratio of the average observed density and the ratio of the critical density is equal to 1. So when they are equal, the universe is flat. When our omega is greater than 1, we'll have a spherical universe. We will have elliptical geometry where a triangle is more than 180 degrees. If it's smaller than 1, we'll have a hyperbolic geometry, which is usually described as a saddle-shaped geometry. However, I describe it as Pringles. So if you ever ate Pringles, that's pretty much it. And okay, did we measure it? Yes, we did. Omega is like 1.0010. So that's pretty close to 1. And if we ask why, we can say, well, it started close to 1, but that's not really an answer. Okay, but inflation, it can say it was exponentially driven to the value of 1. It started small, but it was exponentially driven to it. Okay, you can say that, but it was driven by what? The dark energy, of course. Okay, so the dark energy was the thing that drove omega to that value, and as Professor had mentioned, it is a generalization of the concept of the vacuum energy. And it's the thing we know pretty much nothing about. There are various theories, quintessences, quartessences, and other big words that mean a lot of things I don't know. And it's responsible for the accelerating expansion of the universe. So dark energy, which is not black, I assure you, it's just a thing we know little about, is responsible for the accelerating expansion. So the space has been accelerating from the last 5 billion years. And how do we know that? These 3 guys, Schmidt, Perlmutter, and Rees, they were in 2 competitive groups, High Z and Supernova Search Team or something like that. And they were measuring the so-called type 1a supernovae. And these are the supernovae, hugest explosions in the universe, which happen when a white dwarf, that's a star pretty much at the end of its life, reaches the critical so-called Chandrasekhar limit. And that's the value of when the electron degenerative pressure can't hold the star's own gravitational attraction. It's pretty much the fact when a star reaches 1.4 masses of the sun. Okay, so when a star reaches 1.4 masses of the sun, it's bound to explode. For the rest of us, it's pretty much Christmas dinner. Okay, so they measured these supernovae, and these supernovae were used as standard candles. What does that mean? That means we know their luminosities, real luminosities, and we can see the observed ones. We can measure the redshifts, and we can see what happens. We can see how distant increases or decreases, and so on. And they found out something that pretty much they did not expect, and that was that the universe was accelerating in its expansion. Okay, so it was expanding exponentially, but it was accelerating. And we had to devise a certain theoretical model which would say this is responsible for this acceleration, and we called it the dark energy. And today, of course, it's a thing as if you had a world like we do of 70 to 80% of water, and you did not know what water is. So that's the dark energy today, which comprises 70% of the universe. And pretty much only 5% of ordinary matter. Okay? And this theory has lots of physical implications. One of usual objections is, okay, but where did the inflation come from? Where did things come from? Ex nihilo creation and so on. But I won't go into detail because my first rehearsal of this talk ended up like an hour later, and I'm totally skipping that. So let's deal with the computational one. And the usual objection is, okay, but you have to have this condition and the energy value of this and energy value of that. It's kind of fine-tuned. It really is, but it explains so good these things that it would be kind of shame not to use it as a standard model. Okay, there are, of course, various alternatives to this theory, and there are various extensions to it. And one of the extensions is the so-called eternal inflation, which deals with a kind of island universes. So the inflation never ended in the universe. In some regions it started later, and in some regions it decreased rapidly. So basically you're getting a multiverse theory which has its own problems. And you have certain rival theories, such as the equiprotic scenario, named by Stoics, of course. However, all these theories have their own problems, so we won't go pretty much into this detail. Okay? Yeah, Steinhardt and Milenkin. Blanken were pretty much the proponents of the eternal inflation. And of course, I'm a philosopher. Okay, sorry. Let's continue. So let's come to this part, which is the kind of mystic part, but I like it. So, certain computer scientist a couple of years ago, okay, it's more than this, it's a decade ago, tried to use physical data to calculate the computational capacity of the universe. So the largest number of bits accessible so far, and it turned out to be 10 to the power of 122 bits. So if we were to use quantum computing, and if we were to try to simulate a computer, the whole universe as a computer, we would have to know what are our limits, what are our bounds. And this was one of the first calculations that was made. I went through the proof. It was like 100 lines of code and proof theory, and it took me like 2 months, and it was devastating, but one has to do that. So, of computational complexity. So, computational complexity basically deals with classifying various problems according to their inherent difficulty. So you can say there are some problems for which we have a solution, which is fast and constant, and there are some problems for which we pretty much don't have an efficient solution. We would have to wait for billions of years for the computation to complete. And the two main classes are the so-called P problems and NP problems. The first motivation to deal with computational complexity is the fact that the Clay Institute is offering $1 million prize to solve if P problems are equal to NP problems. So it's cool if you're a philosopher dealing with computational complexities. And the second motivation is that this equality or non-equality pretty much could change the world. So that's cool as well. And P problems. P problems, this is a huge definition, but I'll go step by step, are all decision problems. Decision problems are problems that have a yes or no answer. So, is 12 divisible by 3? Yes, it is. Is 6 a prime number? No, it isn't. So basically, decision problems are met in logic. You have them in computer science and mathematics as well. So basically, you require a yes or no answer for a certain problem. Can I get from Zagreb to Split to Karlovac and so on in the shortest route, which would include this, this, and this? Yes, you can. No, you can't. And they can be solved by a deterministic Turing machine. That means from one state, you can go exactly to a second one. There are no really options from A to B to A to C or A to D. You can go from A to B. That's all. And the third part is the polynomial amount. So I really enjoyed the so-called partition problem because it's easy to illustrate to my grandmother what I'm doing. And say you had a pile of books and you wanted to divide them into 2 equal piles. And these were like books you don't need, like Hegel and something like that. So you wanted to divide them into 2 equal piles and send them to trash. And you wanted to do that. Okay, you would try out every possible combination. Let's try this one and this one, and this one and this one, and this one and this one. And it's a binomial coefficient, but let's illustrate it exponentially. So it's 2 to the power of 100 combination. So if you took a second for each trying out of each combination, 2 to the power of 100 is a greater number of seconds that the whole universe had ever existed. So basically, these problems, which are exponential, which have the unknown in the exponent, not in the base, are exponential. And the reverse is polynomial. It would be easy to calculate 100 to the power 2. Okay, so we are dealing with finding a solution and an efficient way of calculation so we don't die until our algorithm finishes. So, P problems, we can solve them. Computer has no problem with it. For example, give me a list of even numbers from 1 to 10. NP problems are not like that. We can check if the proof is correct. For example, an illustrative example, which is not really correct, but it does picture it quite nicely. It's easy to check if a certain number is prime, but it's not easy to calculate it. For example, it's not easy to calculate a million-digit number, a prime number, but it's easy to calculate if it is a prime number. So NP problems are those which have verifiable proofs, but it's pretty much impossible to solve them. without trying out every possible combination, and that path would take us billions and billions of years. So the greatest question nowadays in computer science and theoretical mathematics is, can we reduce these problems to these problems? Can we find an efficient way of solving them without trying out every possible combination? So here comes the mystical part, brace yourself. Okay. So this was a mathematician called Buzo who calculated that we can use physical systems and cosmological information to calculate to calculate how much are our limits regarding our cosmological models. So he said, okay, I can use this lambda, our cosmological constant, as an inverse, a number of bits that can be used in computation. And he told a story like this. Let's start with our computation at the point P. Let's end at the point Q. And this is the part that is accessible to us. This is the part that we can use. These are the parts that are not accessible to us. Why? The universe is expanding, and everything is moving away from us. And that's pretty much awful for our computation. So if we would like to simulate the universe as a computer, things would kind of start to recede from us, except for Andromeda. Andromeda is chasing us at 200 miles per hour. So not everything is receding from us, but most of things are. So the question is, if we were to use quantum computing, if we were to use cosmological models, could we really solve these problems efficiently? Could we really end up without any resources? So what can we do with it? And there is a certain possibility of doing that. Okay, the first step in every life of mathematical logician is start with your Turing machine. So how would it look like? We would have a tape that would go back and forth, and it would kind of act like a cowboy. So your herd is trying to run away, and you're using your lasso to catch them. So basically, you would have to manipulate all the bits which are close to you, and simultaneously use parallel computing as they try to run away from you. Why? Because we use cosmological models. Okay, so this would look something like this. Things are running away, and automatically the new ones are being created every moment. So, can we really solve NP-complete problems? So let's say you end up getting up one day and God lost his keys somewhere in the universe. Okay, so please, you're a computational complexity master and you know some cosmology, a really small part of cosmology. So can you help me? There's somewhere in the universe, I can't really remember where, so let's find it. Treat the universe as a database. Okay, so if we had a Turing tape with one dimension, we could do that. However, when our dimensions decrease, we can only check the square root of possible locations, either as the square root of 1 over lambda, and so on. And the question is, okay, if I were to simulate quantum computing, if I were to simulate the universe with its vast resources, the universe which is driven by this dark energy which started with the inflationary era, can we really solve it? Can we really solve it can we really use it as a role model for our computation? It doesn't seem so. We can use certain quantum algorithms with probabilistic answers. So there is the most famous one, which is called the Growver Algorithm. And there are various algorithms such as random walks, in which you, at every part of your graph, at every part of your walk, you calculate the probability distribution. So one of the possible answers, which I was pretty much shocked to find out, was, okay, try out every possible combination, and after performing the calculation, kill yourself. There is an inflationary universe where you got the answer wrong, and I'm not going to do that. So basically, we can stick with the fact that it seems that even if we had all the resources that were existed in the whole universe and that will exist one day, it seems that it won't be enough. Okay, so God, sorry, they're somewhere. Maybe they're over our cosmological horizon. And the question is, okay, how much of the observable universe could we take advantage of before our tape proceeds? Because everything is moving away from us. So we could try, but it would not be really efficient. And what does that imply? That implies that even though we don't know theoretically to prove that P problems and NP problems aren't really equal, we can say we have physical restrictions to it. It seems that we really cannot. Why? Because we had calculated that there is an upper bound to information, to processing information, to computational complexities. And as our n, as our input grows even larger, it won't be enough for us to solve efficiently NP-complete problems. So there is not really a deterministic algorithm, and it may seem that NP problems could not really be reduced to P problems, but there could be a probabilistic one. And nowadays, people really use various probabilistic algorithms to solve NP-complete problems, because pretty much every cryptographical program today uses a certain kind of NP-complete problem. Why? Because when you log in into your Gmail or Yahoo account, if a hacker would try to go through to your account, it would have to try every possible combination in order to do that. And it's the so-called brute forcing, and you pretty much don't have the time to do that. So if we combine the cosmological models, and if we see that the whole resources of the universe aren't pretty much enough, and that we have an upper bound on our computation, it could give us a practical, empirical approach to say, okay, we probably have this NP bound as a certain quasi-physical law as well. So the huge implication is, if we look at the world outside, it will tell us that that P is pretty much not equal to NP. However, there is still a proof to publish, so here you go. I won't do that, but good luck. And thank you for your time. I hope it was not an exponential one. So if there are any comments and questions, I'd be happy to try to answer them and probably fail. So, thank you.
Questions? Comment, okay.
Rather about the computers. The universe is actually a terrible computer. Because the size is so huge and you cannot communicate between the elements of the computer. So the idea is to build small computers and not big computers. Another problem is that the information stored in the universe can be huge, but it is limited by the area of the horizon and not by the volume of the universe. So it's a holographic model. Yeah. Thank you.
You want to comment? No? Okay. Mark Mušić. You want to say?
Well, at first, I would like to congratulate you for this interesting presentation. Well, it was exciting in a way, and so, well, but still I have some questions. Your presentation was, so generally speaking, was combined of two main topics. One topic was inflation theory, and the other was all the story about decision problems and so on. Maybe you can explain something more how these two topics are combined. What is the missing link here? What is the middle term between them? I didn't catch quite enough this point. And especially in the end, when you mentioned this upper bound. Well, here I didn't catch quite good. Was it meant an upper bound of what? Of algorithmic approach or of horizon, or what is it actually? This what was meant by this upper bound? Because in your abstract you have here also you didn't mention so much that one of the consequences of inflation theory is, of course, that the universe is much bigger than our horizon, Hubble sphere. So is it meant the question of horizon here, or a question of algorithmic decidability from Gödel and up to, let's say, Penrose, who is against this algorithmic possibility of everything. He says that everything is not decidable and so on. What was actually meant and what is this connection?
Okay, I'll start before the questions start receding from me. The first, I believe that it's a standard practice in academic community to write an abstract and then pretty much not follow it, so sorry about that. Because you're doing it like 5 months earlier and you have no idea. Okay. The second thing is I had no time, and I'm really sorry about that. There is a huge thing called the Birkenstein bound and the holographic principle, which kind of explains this into detail. And I wanted to just pinpoint a few main topics of it, and it deals with quantum computing. And these are the missing links. However, the formulas scare me. I kind of went through them, but if you would like, I would pretty much be glad to discuss it with you in more detail as well. So there are certain pinpoints, such as the Birkenstein bound, holographic bound, which deal with entropy. They started with calculating the entropy of black holes, and they use it as a maximal information. You can use it as well. So basically, this is the kind of the missing link. However, I really did not have the time, and I wanted to spend as much time I can on inflation because I'm in love with it. So I try to run away from my PhD research as much as I can, so this is the missing link. And thank you for your compliment, it really means a lot.
Yeah, but I still don't know what is the connection actually between the theory of inflation and this decision problem and all this story about informations and entropy and Seth Lloyd, you mentioned Seth Lloyd, his famous book.
Okay, Lloyd's research was motivated by the fact that the quantum computing was starting to develop. Okay, we would have to see how can we use this quantum computing to solve these problems efficiently. So one of the areas, which was kind of a motivation for it, was to use the physical data that is near to us. We can use cosmological models. Let's try with something that is familiar to us, and then we'll try some magic. Then we'll do some quantum magic. So basically, they started doing the cosmological research, such as Scott Aronson did. And Scott Aronson started this, and I kind of tried to finish that, pretty much not really successfully, but okay. So he started doing this research of combining various cosmological models as a certain role model for quantum computing. And we're not pretty much sure that it would be useful. So at least we know it would not work. And this is one of the things that pretty much won't work, but it's nice to see how it could work. And it's nice to see that if we were to simulate the inflation theory and use it in quantum computing, we would still not be able to solve NP-complete problems. And that would mean huge implications for computational complexity as well. Why? Because that means that with a high level of probability, you probably won't be able to do it in real life as well, because you use real life as a role model, and it fails in your model, which is based on the real life. So that pretty much gives us a nice clue of saying P problems really are not equal to NP ones. Am I being clear, a bit clearer now? Yeah. Okay.
Tom, sir.
Okay, thank you. In fact, I have essentially a similar question, but then I have another question where you were talking about non-P, non-polynomial and polynomial problem, which is really in mathematics not solved whether it is the same or not. But can you comment on that question? Quantum computers, which some of them promise something that they might solve non-polynomial problems.
Okay, they do promise, but they don't deliver. That's the prime of a problem today. Quantum computing today, which doesn't use physical resources as the role model, use only probabilistic approach. So you have two main species of algorithms. The first one are the so-called probabilistic ones. So quantum mechanics pretty much is a probabilistic theory. So you use this as your guides, and you say, okay, it's a high level of probability that the solution is close to this. It's a high level of probability that the solution is close to this. It's yes with like 99%. high probability. So the other part uses the so-called non-uniform algorithms, and this is the kind of the newest trend. And pretty much people use these non-uniform algorithms, so they use different input every time. Your input size changes at every step, and it ended up pretty much catastrophically. This is the newest thing, and we're not quite sure how it's going to end, so watch out for these algorithms. However, the quantum computers are not really promising anything nowadays. They're
the problem which you mentioned, which is non-polynomial, it can be proven mathematically that quantum computers, if they work, they will solve that problem. That particular problem is soluble.
In the certain so-called oracle situation. If you had an oracle, it would be solved in that case. However, we had not come to that case in which would be solved. So it's a promise, but it's still a promise. It's a promise that I had given as well. And wait for another 13.8 billion years and we'll see who will deliver. So basically, you're still ending up with probabilities, and you're still ending up, in the case if we were able to simulate it like this, we would be able to solve it like this. That's not really a promising theory, because it has lots of ifs, and that's kind of sad.
Some other questions? If not, then, oh, yeah. Jean-Marc Leblanc.
It's just a very small question concerning a purely informative fact. What do you think of the recent paper which was published at the beginning of June, claiming that the evidence for the acceleration of the universe is much less strong than was believed before, taking into account the much larger number of supernovas we have now in our data set?
You don't have to comment.
I will just repeat Professor Bilici's words that that could be a possibility, of course. We are open to falsifying every possible theory we have. We were pretty much shocked to see that the universe is expanding at an accelerating rate. And I would be pretty much amazed to see that. And however, let's wait for 10 years. Sol Perlmutter and Rees ended up their research in 1998, and they got their Nobel Prize in 2011. So we have to see if a certain time passes to see if it really holds. And if it was published in June, I certainly did not follow it, but I will. And I'm looking forward to reading it, and it would have huge implications, of course. It would have a nice implication in my theory, which would pretty much mean you don't have to deal with it anymore, so win-win situation, really.
Some other questions? If not, then thank you very much.
Thank you.
We pass to the next lecture by Domagoj Kujić about the probability and statistical mechanics. Is it already prepared?